My name is Hubert. I'm a Ruby developer. You can find me on Twitter, on GitHub, on other services using Hubert Łępicki handle. I really like being followed on Twitter, so you can do that. I have a privilege of working at Amberbit. We're a Ruby Rails development shop. Originally, we're doing a lot of Elixir, a lot of JavaScript as well in the recent years. And today we're going to talk about fault tolerance and a few related concepts as well, especially scalability and concurrency, because those two subjects, they come together with fault tolerance usually, and the same tools can help us sort out both issues. And we're also going to do some time travel. I'm just going to move the cursor away. Which is always fun, right? In Star Trek, time travel is always fun. Okay, let's start with fault tolerance. So we have a few definitions. And first, let's go to the random wisdom of random people at Wikipedia. And they define fault tolerance as a property of software that enables system to operate properly even if the failure occurs. And there's a few definitions like that. I don't really like those. Some of those definitions say that fault tolerance means that the system should be working properly even if the failure, or be working according to specification even if the failure occurs, which rarely is a case. You can, because the failure occurs, so it no longer works properly. So what I like to think about fault tolerance in a way that this is ability to detect and recover from software failures. If we can detect and recover from software failures in automated manner without waking up developers at 6 o'clock in the morning on Saturday, that would be perfect. So the question is whether we can do that and whether we can avoid cascading failures where our systems fail for all of the users and our business just not making money. However, we can serve some pretty error pages or less pretty. The thing about fault tolerance is that it's definitely a hard thing. It's one of the hardest things in computer science. To illustrate how difficult it is, we should go back to the year 1992. And probably we can skip those guys and just focus on those two instead. The man on the left is Linus Torvalds, creator of the Linux kernel. The man on the right is Professor Tannenbaum, who has been creator of the Minix operating system. We probably all know Linux. Maybe we have more Linux kernel instances running here than the people on this audience, because there's plenty of Linux kernels in our phones, etc. Minix is also still alive. It's an operating system being used for teaching design of operating system or teaching the basics of operating systems. And those two guys, they got into a quite ugly fight, online fight. If you know, Linus Torvalds is pretty opinionated and uses very much strong language. And that's how this fight enrolled in 1992 on Usenet. They exchanged some opinions, and obviously Linus Torvalds, he said, okay, we're just going to build the simplest possible thing that's going to work for most of the users, because building the operating system the way you suggest, Professor Tannenbaum, is really hard. Professor Tannenbaum argued that he wants to build an operating system, and operating system kernel should be built in a manner of services that operate semi-independently and exchange information to provide fault tolerance and resiliency to stuff like hardware failure or software failure. Linus said, okay, that's stupid because that's well, too much work to do it. One of the sentences that caught me when I was reading that discussion was that in 5 years, that none of that's going to matter because we're all going to use GNU kernel on our fancy machines, and the GNU kernel was actually being developed at this moment according to the microkernel principles. So it was meant to be fault tolerant, and it actually is still being in development after so many years, and doesn't support many features that modern operating systems we expect them to support. So the conclusion is that GNU Linux won because it was simply simpler. It was providing the useful advantage in contrast to GNU, which took a long time to develop and still is being developed. Even though, if it fails, it fails badly. So if there's a bug in the operating system driver, for example, that writes to memory in the wrong place, it's just gonna crash in a unhandled manner. And sometimes, as apparently this example shows, that's okay. Implementing fault-tolerant systems costs something. Sometimes it costs multiple things at the same time. So it costs money, it costs time, effort, it can increase complexity. So before we actually dig into doing that, we might want to start with small steps and just ensure that our system is written to provide business value, and then we add some minor tweaks to it to make it slightly more fault tolerant, and that's okay. Small steps work. In Ruby, we have some basic defensive techniques against software failures or external components failures. And they come in forms of two things that we can use out of the box. One is obviously the exceptions. If something goes wrong in Ruby, or in Ruby library, or when contacting external service, at some point an exception is going to be raised. An exception is just an object that contains some useful information that's being thrown at some point, on some level in stack trace, and somewhere above in the stack trace, hopefully we're going to catch it. So whenever you're doing an operation that can fail because of a network error, because of a bug that you expect maybe there is, you should definitely wrap it in exception handling. And exception handling is pretty convenient in Ruby. You can catch multiple exceptions. Exceptions do have a hierarchy of inheritance, so you can catch a parent exception to catch more exceptions, or child exceptions to be more specific. You can have multiple clauses to differently react to different exceptions if you want to. Or something that people often forget, it allows you to do a simple retry. When an exception is being caught, you just retry, and probably makes sense to have a counter to fail badly after a few retries. That can be useful if you're trying to download something from external service, or in case of one-off errors that you don't really control. One of the techniques I like to using is that exceptions often, the blocks that define exception handling, they are like Ruby blocks, so they return some value, they are expressions. And often you can do just that and then handle in your code the value when it's nil, so the file couldn't be opened in some case, and your system is already resilient to failure in terms of opening file. A good idea to detect exceptions is to actually log those exceptions. If you have a logging facility in your system, you can hook it up to the exception tracking, and you definitely should log and possibly warn you when the new exception happens. Stuff like rollbar can be very much useful to do that, or any other exception tracking software out there. The other thing that I like to build is to separate those parts of the system with what you can call bulkheads. This is actually the term that Avdi Grimm uses in his book Exceptional Ruby, which is a good read, by the way. And the bulkheads are just blocks that catch some that isolate some operations, some pieces of software. So whenever an exception in that piece of software happens, it's going to be caught, it's going to be logged, and possibly you're going to recover from this exception. Especially if you're contacting external services, you can use combination of timeouts to make sure that the operation, the external operation, doesn't take a lot of time. You do want to interrupt it if it does, and exception tracking. So the timeout is another thing in core Ruby that you can use to basically interrupt long operations that take surprisingly long time. And why would you want to do that? Is to prevent cascading system failures where the system becomes inoperative because it's stuck on those external long time consuming calls. It's especially important if you have a traditional Ruby deployment where your web server spawns, I don't know, 5, 6, 7, 8, 12 system level processes, and each of those processes handles one thing at a time. So it only takes 1, 2, 3, 4, 5, 12 requests that get hanged on calling external service that takes a lot of time to block your whole application for all of the users, not just for the part of the application that is being affected. And simple bulkheads, like I showed before, might not be enough to do that for many reasons. But most importantly, once the failure of external system has been detected, you most likely want to fail fast so that you don't wait these 20, 30, or even 3 seconds if you have a timeout on each request, so you can serve other requests in the meantime, leaving that part of the system not working, but maybe this is not the most important part of the system. I don't know. It might be just checking your subscription or uploading avatar or downloading some images. You don't want some things to block usage of the system for the whole users. So you want to crash those things fast. And there's a pattern to do that. You probably are familiar with those little things. These are called circuit breakers. If you live in a flat house, wherever, you will find them somewhere in your apartment. They are intended to prevent bad things going really, really bad in terms of your electrical wiring. So if you have a short circuit, I don't know, in your laundry machine, it will detect it and open the circuit so that it doesn't, so your laundry doesn't catch fire, for example, and your house doesn't burn. Or if you put your fingers into wall socket, you don't die because it's gonna open the circuit. The same thing we want to do in our software when we call external services. We want to immediately detect the failure and open the circuit, and that's all this pattern does. In classical example, we have 3 states. We have closed circuit state. Usually there's a proxy object that wraps the calls to external service, and it keeps the state. So when the circuit is closed, all the requests are being passed to external service or being passed to this part of the system that we want to isolate. But when the failures, they start to occur, they're being detected and they're being tracked. And there's usually some heuristic to detect, to figure out when to break the circuits. Like, for example, if 3 failures to external service occur within 20 seconds, that means this external system is probably down, so we open the circuit. And then after a certain timeout, we switch it to half open state and just pass 1 request. And this 1 request, if it succeeds, means that the external system has been fixed. So we can close the circuit and pass all the remaining requests. If it fails, we leave the circuit open and try it again in a few seconds. there's a really nice barebone library for Ruby called exactly that, circuit breaker. The usage is that simple. You just include the circuit breaker in your wrapper that you probably already have that calls external service. And it's using some smart meta programming behind the scenes to wrap your methods into exception tracking and make them fail fast once it detects failures. However, the usage of this particular gem can be pretty much limited, and because of the nature of the Ruby web applications that usually spawn, that create all the objects from scratch on every request and then discard those, so you have to persist that object between the requests, or if you have multiple processes, it's not gonna synchronize the circuit state between those processes by default. But there are other libraries like that. This one is just the simplest to use. The guys at Shopify, they released, one of the open source projects they released is doing exactly that. It's called Semian, and they call it Resiliency Toolkit for Ruby. It's basically a circuit breaker on steroids. In addition to being able to detect failures, you can also limit the concurrency when you request some stuff from external services. So it has like a ticket system where one ticket is given to the process that wants to use the external system. It's specifically designed to work in traditional Ruby ways where you have web server like Unicorn, and they are not threaded servers. They're like not Puma, but they're unicorns, for example, and they don't share memory. They don't do threads. So it's being built on top of system file, Unix IPC, and especially semaphores to synchronize the execution and signalize whether the circuit has been opened or closed. What's cool about it is that it's a bit lower level than the library I showed you before, but it allows you to hook into existing software to make it fail fast. So if you have a library that you use to use MySQL, for example, you can use this gem to make it fail faster once the connection doesn't work to the MySQL, and synchronize that across all of your workers. The other cool example of using that is when you have a library that's using some external services, consumes REST services, etc. It can hook into net HTTP library, and in that particular case, we're tracking all the requests to wroclawrb.com website, and if they're gonna start failing, we're just gonna start failing fast. And when we use this library, this is gonna affect all the other libraries that rely on a net HTTP, which is basic Ruby HTTP library. So it's pretty cool. How else can we make our software, Ruby software, more resilient to failure is to break it down into smaller chunks. You can call those microservices or service-oriented architecture or whatever. You just break it up into multiple applications that somehow communicate with each other, and they can be monitored independently, they can be restarted and deployed independently, so you get a little bit of more flexibility. And we did, one of the projects we did exactly that. We just broke one application into 3 parts where we had a web interface, we had some sort of archive, and we also had some sort of workers pool. They were all connected using RabbitMQ, which is quite good and easy to use messaging queue. However, we did definitely something wrong by doing that, because we started noticing failures, and those like ghost failures that happened usually after the weekend, and nobody's using the app during the weekend because it's a business software, so everybody sleeps. And when they come back to work in the Monday morning, it suddenly stopped working. There was something voodoo was happening. Like this is like the Schrödinger's cat. When you look at it, it's working, but when you stop looking at it, it breaks. So difficult to track, right? And it turned out it was a misconfiguration of how we connected to RabbitMQ, and we spent many hours trying to track it. It just boiled down to fixing that one line that disabled the heartbeat. What was weird about it was that the TCP connections, they were open, and they remained open on both ends, on all ends of the system. So clients and the RabbitMQ server, it thought that the connections are open, but messages were not arriving. And the reason for that was that the infrastructure we used forgot about those connections. It garbage collected those connections without telling anybody. And that's what the routers, firewalls, or the cloud, like on Amazon, they just do that. They will detect those idle connections. They will get rid of those idle connections without telling you. And apparently, we enabled the heartbeat. And the funny thing about it is that it takes up to 25 minutes for the operating system to detect those sort of idle connections. And if you have a pool of 20 workers, that just multiplies, so that was our problem. But anyway, let's go back to the core of this talk. And let's have a look again at the GNU kernel logo. You can clearly see those elements that are separated. They communicate through message passing. And you saw my beautiful diagram where we had the RabbitMQ here, and this same thing, right? So you just elements, it's building blocks that communicate somehow, and there's clear pattern that arises here in terms of how you should handle concurrency. And there's a really good implementation of that pattern out there that helps you. To understand it, let's go back to your 1986 this time. Here. So in Erlang, in Ericsson, Ericsson built those phone hardware where you could just dial in and have a conference call, or it's supposed to handle hardware and software aspects of establishing, handling, detecting, and recovering from failures when the connection failures occurs as well. So if you think about it, those telephones, they had to, or those hardware that dealt with those telephones, it had to deal with similar problems that we have to deal when we build especially distributed software. And Ericsson engineers, they came up with new runtime and new language called Erlang. This research they put in has been turned into a PhD thesis for Joe Armstrong, the original creator of Erlang at some point. It's a good read. It's not very sciencey, so everybody can understand it definitely. They don't use fancy words to describe what Erlang actually does. They don't use scientific terminology. But basically, Erlang implemented what is called actor-motor concurrency, where the basics, the building blocks of the software are the same as the building blocks of the concurrency, which are called actors. In Erlang, they are called processes, but it's the same thing. And actors communicate only one thing, in one way. They can send each other messages and receive messages. On top of that, to make that sort of concurrency possible, we want to those actors, they can fail, so they can crash. We want them to fail if there's an error. We don't want to write much of defensive programming in Erlang, so you just let those things crash. But instead, the runtime provides you with a possibility to detect and react to those sort of failures. So whenever something in the system, an element crashes, something else is going to be notified. And this something else, some other actor or actors in the system can either crash as well because they are connected to each other, notifying other elements of the system, or they can be fixed. And the usual fix is, like everything in IT, you can simply just restart it. That's the simplest way. And actually that works in many cases. And this built-in mechanism to recovery is called supervisors. Let's see how that works. In actor model concurrency, in the Erlang flavor, you build those sort of dependency trees between, it's called the supervision trees of the processes, these actors. They talk to each other, and they all depend to each other. They have linkage between, so when one node fails, it can fail other processes, other actors. Something else can detect that and can fix that. So can bring back the system to the normal state, to the last known working state, for example. And that's exactly what we want to do. At the same time, we can kill two birds with the same stone, because we're using concurrency. We can make our system more scalable and concurrent by default. And this is a message passing. Messages are immutable, so we can put those processes on different hardware, and they will communicate over network. That's ideal. And this is so good, so appealing to many programmers, that it has this form of programming has been adapted into many other programming languages. That includes Java, that includes .NET, obviously Erlang and all its children, like Elixir, inherited that as well, but you can even find libraries for actor model concurrency for C++ or C or Clojure. Is there something like that for Ruby? Of course there is, and you probably heard about it. One of the libraries that facilitate actor model concurrency and allow you to build more fault-tolerant systems is called Celluloid. It's been out there for many years already. Sidekick, the library that handles background jobs in Ruby, used it for many years. They finally decided to get rid of Celluloid and replace it with handwritten their own architecture to get rid of one dependency and also fix some performance issues that Celluloid did have at the same time. However, the original author of Sidekick still recommends using Celluloid if you want to build something like Sidekick at first version. And it's really user-friendly library and provides a lot of, it's appealing to a Ruby programmer because you still operate on objects. So for example, if you want to turn some object into an actor, so it's gonna be started in a new thread, all you have to do is to include that Celluloid into it, and then just create new object, and behind the scenes it's gonna create a new thread for you. And you can send it messages. In Ruby, sending messages is equivalent to calling functions, so it looks like you're calling a function. Behind the scenes, there's a message being sent to this thread. It lands on its inbox queue, and it's going to be processed at some point by that thread, which is a really nice abstractions, nice abstractions, and it gives you a way to call those methods synchronously, waiting for reply, or asynchronously, just fire and forget, which is also really nice. In addition to those sort of things, when you have an actor model concurrency in Celluloid, one of the nice things I like about it is that it allows you to hook into tracking all of the exceptions. So whenever there's an actor, if you use normal threading in Ruby, you have to work really hard to implement all of the exceptions, because the exceptions can happen at any point in a thread, and they don't propagate to other threads until you call join and stuff like that. So, so Celluloid fixes that. You can just provide it a block and log all of the exceptions that happen in any of your actors with an ease. In addition to that, it allows you to supervise and fix broken actors, so if they crash, Celluloid has the ability to restart those. Right. There's also another library which is being, if you migrated to Rails 5, you most likely have it included in your gem file. It's called Concurrent Ruby, and it's being used by these. How is this thing being called? This WebSocket thing in Rails 5? Yes, action cable. So it's being used by that. In the first version, they used Celluloid, by the way, but they also get rid of Celluloid. So there's a pattern here that people migrate from it for some reasons. And this library is supposed to be less opinionated and have a bit of a broader perspective, not just having a look at Erlang, but also having a look at other systems. But it also has the ability to do actor model concurrency, supervise those things, etc., etc. And it's being developed by the same people that developed Truffle Ruby, which is other interesting thing to discuss at some point. Truffle Ruby is going to be the next big thing, I think, in Ruby virtual machines. Let's see how it plays out. All right. Last time travel. Now we're going to move forward to the year 2020. And we're probably not going to get those anytime soon, which is a shame. But in the year 2020, we're promised to receive Ruby 3.0, which is going to come with some new mechanisms to handle both concurrency and scalability and fault tolerance in forms of guilds. It was proposed a year or 2 years ago at Ruby Keiji on the conference in Japan. I think it was proposed then. And the guilds are directly inspired by the Erlang and Elixir specifically. They are being mentioned in the presentation that this has been inspired by Elixir. And they bring also some elements of immutability to Ruby programming language. So those messages that being sent between those actor things, they are immutable, or they have to be moved from one to another if we want to have them mutable. And they basically wrap the existing functionality of Ruby into another block. You know, there's no problem that you cannot solve in programming with just adding one more layer of abstraction, right? So that's what the Ruby core developers are doing here. They're just wrapping everything we have now into one more layer of abstraction, one more sandbox, and allow programs to run in those sandbox, and they just will have limited capabilities to communicate by sending themselves messages, which is really nice because it isolates those elements of the system. And if one of those fails, it's not going to do a cascading failure. We might have, we might build tools because the Ruby is not going to provide them to monitor those guilds as well and fix them if they crash. If they crash badly, we just restart it, or maybe we do something else, monitor it. So it clearly looks like an actor model concurrency at some level. But the nice thing about it is that it's going to fit very well with existing apps. So you will be able to run your current programs like you do now. They're just going to eat up one guild. And if you just want to extract something to another piece of code, you won't have to do it like we did. So set up a new instance somewhere on the server, and the message queue is not going to be needed because it's going to be built in here. So, so this is definitely a progress. And I hope they're going to simplify the concurrency and make our software more resilient to failure. Okay, I think that would be it. Just a few words about resources that I used during this talk preparation and that helped me before. There's a really good book, Release It, on pragmatic programmers, that describes a few things, some quite similar to what happened to me, so I was smiling while reading it. About it doesn't give you an examples in Ruby or another programming language, but you know it's a good read anyway. And Ruby itself, a small book by Avdi Grimm, Exceptional Ruby, a really good one, and more of a formal one, Patterns of Fault-Tolerant Software. I had a peek there as well, learned something. Good article about circuit breaker pattern by Martin Fowler on his blog from 2014. Again, this PhD thesis is really nice read about Erlang, gives nice overview. This is a really good book about Erlang in general. So whenever you're learning Elixir, Erlang, etc., you should definitely read it. It's a fairly fresh thing. And it gives a lot of insight on how actor model concurrency and failure detection recovery works in Erlang. And the proposal, there's a link to the video to these guilds in Ruby. That's it. I'm going to put it online so you can read it. I'm going to tweet it in a second. So thank you very much.
Thank you. There's the first question.
So both Minix and the GNU kernel are based on message passing and are supposed to be fault tolerant. So what's the reason nobody is using them? And everyone is using Linux, which is not fault tolerant?
They're not ready, they're slower. There's a penalty in terms of performance as well. But most importantly, they're not ready. Minix, when Linux was a hit, when it was being used instead of any other kernels, actually shifted to teaching software exclusively, so they don't intend you to run Minix on the computers. And GNU kernel has been in development for many years. They don't know what to do about it, to be fair. They just, they were thinking about replacing it with other kernels, maybe grabbing something existing, maybe, you know, there's a lack of manpower definitely to implement it. It's a complicated task.
Any other question? Nope. So thank you once again, Hubert.
Thank you.